Pleasure to introduce our very own Jill VanTongeren. Jill got her bachelor's degree from the University of Michigan in 2004. She got her PhD from Columbia University at the Lamont Doherty Geological Observatory in 2011. And her dissertation topics, she had two, and one was working on the Bushveld igneous intrusion, the largest layered igneous intrusion on planet Earth. Another dissertation topic was on the lower crust of the lower oceanic crust in the Oman Ophiolite in Oman. And after she graduated in 2011, she did a postdoc at Yale University from 2011 to 2013. And it was during the time of her last year at Yale that I met her. And it was also that year that we had the great fortune of hiring her as an assistant professor at Rutgers University. Jill continues to do work on the Bushveld intrusion, and she's doing some very exciting stuff. She is mentoring two PhD students, Jake Satera and Aidan Taylor. Aidan is working on the Dufek intrusion in Antarctica. So I guess we're probably going to get an update about the latest thinking about the Bushveld soon enough with Jake's thesis, whenever he's going to defend. And so today, though, Jill is going to talk about her work and on the oceanic crust. I guess it's in the Oman.
Yep.
Thank you very much, Jill.
Thanks, Claude. Well, Claude sort of foretold the future of the next couple of slides of my talk. So I will sort of rehash what he just mentioned, is that today I'm going to talk to you about some work that I've been doing, some exciting stuff that I am mostly been interested in the last couple of years, looking at temperatures and timescales in the lower oceanic crust. And I gave a talk here like 3 years ago for my third year review. And in that talk, I tried to talk about the four main field areas that I've been working on, the four main topics or themes of my research. And I tried to give you guys each like 15-minute sort of AGU style presentations on each of these four different themes. One being layered intrusions, the other mid-ocean ridges, oceanic plateaus, and early Earth tectonics. And that went over okay, but today I decided that I was going to give you more of an in-depth look at one particular study that I'm really excited about. And I will leave the rest of these sort of topics for future talks, but I will mention a few things because, as Claude mentioned, I've been working extensively on the Bushveld layered intrusion and layered intrusions in general. And my two PhD students, Jake Satera and Aidan Taylor, have been working or have projects on these two layered intrusions. And I kind of wanted to highlight their work and their efforts in this talk today too. So here is Jake next to the UG1 chromatite layer. It is a World Heritage Site in South Africa. The UG1, UG2, and Merensky Reef chromatite and pyroxenite reefs are some of the world's largest platinum group element deposits that we have mineable today. So the Bushveld accounts for nearly 70 to 80%, depending on whose numbers you trust. 70 to 80% of the world's platinum proven reserves in the world. So these are very, very important magmatic deposits, these layered intrusions like the Bushveld, to understand economic geology processes as well as what's going on in magma chambers deep within the Earth's crust. So this is the Bushveld here. You can see it in the orange. And this is South Africa for scale. And I like this because you can see that the Bushveld complex is incredibly large. And the Bushveld itself, in those two like lobes, western lobe and eastern lobe, is actually 9 kilometers thick of magma as well. And so we've been looking at what are the thermal causes, or what is the thermal response to such a gigantic, massive outpouring of magma in the Earth's crust. And what Jake has been doing, and I'm going to let him highlight a little bit more of this when he gives his colloquium in December, I believe it is. But what Jake has been doing is looking at how do these big magma chambers like the Bushveld complex cool and crystallize with time. And to do that, he's employing a wide range of geochronology and geothermometry. So in particular, uranium-lead ages in zircon, as well as argon-argon ages in amphibole, biotite, and plagioclase. And the great thing about these different systems is that the uranium, lead, and zircon traps in an age when the magma reaches about the 800 to 900 degree isotherm. Okay, so that's the crystallization age that the Bushveld, this large magma, is going through. And the great thing about argon-argon is that these are trapping in ages at lower temperatures. And so if we know the age of the zircons at 900 and we know the age of the plagioclases or the biotites at 200 or 300, we can kind of constrain a cooling rate to get between those two ages from 900 to 200 or 300 degrees C. And Jake's made a lot of progress on this. Very exciting results, and I'm going to let him give you those results and not, spoil his fun for December. But I also want to say that this work has also involved several Rutgers undergraduates since I've been here. Caitlin McCloskey worked on aspects of diffusive chronometry, diffusive thermometry using iron titanium diffusion in oxides. Laura Salmon worked on aspects of the overlying rhyolitic lavas and what temperatures those were erupting at. And Ria Sathwara is working with me currently looking at diffusion of calcium in olivine, which you'll learn a lot about in this talk as well. So these are all part of this larger project of how do these big magma chambers cool and crystallize, which has huge implications for things like how do platinum group element concentrations get formed in the earth and where can we find them in other places. I want to also highlight Aidans' work. So here's Aidan working diligently trying to separate out zircons in the clean lab down at Princeton. Aidans' work has to do with another big layered intrusions that we haven't been studying very frequently in the past because it's in Antarctica. It's called the Dufek intrusion. And the overarching goal for Aidans' work is to look and see, or the original overarching theme was to look and see whether big magma chambers like the Dufek intrusion and the Bushveld intrusion crystallize and cool faster than small layered intrusions like the Skaergaard intrusion, for instance, in East Greenland, which is also well studied. And so we collected a bunch of samples from the Polar Rock Repository in Ohio that have been collected ages ago in Antarctica. And Aidan is working at getting some new crystallization ages, uranium-lead crystallization ages from that. And because Aidan is not giving a colloquium anytime this semester, I just wanted to quickly show you some of the new exciting results that he's been getting. So based on this is pyroxene Mg number. Unfortunately, the slides are getting cut off at the bottom. This is pyroxene Mg number, which is sort of a proxy of how new or primitive a magma is. So if you have a high pyroxene Mg number, it means you're new or hot. And if you have a low one, it means you're older, more evolved, and cooler. And based on this, we sort of assumed that we would see a progression of ages from young in the beginning old in the beginning, and younger as you go up. So you can see the crystallization happening from the bottom of the pile up to the top of the pile. And his data has turned out to be exactly the opposite of what we had expected. And so these are really exciting new results that we did not predict we were going to get. And we think that there might be two potential explanations. So one is that the two exposed sections, we've got the Forrestal Range, the upper portion of the stratigraphy, which is separated from the lower portion of the stratigraphy by a snowfield, which we cannot melt in the next 10 million years probably. So we're separated here, and it's not clear. It's clear from the dips that they may be connected at depth, but it is still not certain because we don't have the exposures at the surface. They're buried. So it's possible that these two sections are actually two different intrusions, all part of the same Gondwana breakup magmatic province called the Farrar-Dolerite system. So it's possible that these are two different intrusions separated by a couple of 100,000 years, or that these zircon ages are actually recording a cooling profile and are not recording the crystallization of the intrusion, but are instead recording sort of the last gasp of that liquid being solidified as the cooling front sort of takes place. Okay, so these are two things that Aidan is going to be working on in the future, sort of refining and filling in these gaps of ages. He's gotten a few more from up here, which also are looking very similar. And we're really excited about this new data that's coming out on this project as well. So I will stay tuned for that. Jake is going to talk a lot more in detail about that at the end of the semester. And then I'm sure Aidan will be willing to share lots of his thoughts on these problems in the coming months or semesters as well. Okay, so to get back to temperatures and timescales of crystallization in oceanic lower crust, the Midocean ridge system accounts for approximately 60% of the Earth's surface and between 75 and 85% of the global volcanism that we see on a yearly basis over the last 180 million years. And unfortunately, I really wish I could just yank this thing down so you could see the rest of my slides because there are important things down at the bottom, but we'll deal with it. Can we forcibly move it? Because we can't do it on the computer. There's no way to do it.
It's beyond my reach.
If there's a stick. One thing that I did last year when I was running this was to, the other sides don't seem to have a problem. So it's possible. I don't really want to mess with it. I don't really want to mess with it now that we're, in it here, but.
So if you pull in it, it doesn't work?
I can't even tap anything anymore.
Ooh, this is sliding off.
Local mode. One thing that did work in the past was to have the other two sides come down, and those have at the bottom.
Welcome to Rutgers.
If I end a session, is it going to ruin everything?
No, it will make it better. Go for it.
I can't even touch it.
It's not a touch screen.
Oh.
That's okay. I did the same thing in food science the other day.
Okay, anyways, Midocean ridges account for a lot of the volcanism that we have on the planet today. And as such, they are obviously very important drivers of global geochemical cycles. So not only in terms of mantle and lithosphere processes, but also in terms of global climate. The Midocean ridges account for tons of volcanism on the planet, and they have an important role in hydrothermal circulation and temperatures through time of the atmosphere and seawater. Hopefully these will turn on. They're starting up? Okay. Anyways, so because they are such important features of the Earth, we have obviously spent a lot of time and money going out to sea to try to understand these things. And we understand pretty well the structure of the oceanic crust now. There's still a lot of details to be worked out, but we know pretty much that we have divergent spreading, which releases magma from the mantle due to decompression melting, which then makes its way up into the crust. We have about 4 kilometers in fast-spreading ridges, at least 4 kilometers of gabbroic material, so intrusive basaltic volcanism, followed by about 2 kilometers of extrusive basaltic volcanism. And we know pretty well what the composition of that is, and a lot of cruises have gone out and measured a lot of the chemistry. But the problem is that we really only have access to the absolute top, because when we send a dredge down or we send a drill down, we really can't break through that 2 kilometers of basaltic volcanism up at the top to be able to see into the lower oceanic crust. And so in my mind, there are 2 major outstanding questions that we still have not resolved in Midocean ridge research so far. And that is, number 1, what is the thermal structure at the ridge axis? Is it hot everywhere? Is it hot only at the top? Is it molten all the way through? And if not, how much of it is molten at any given time? And the second question plays off of that last thing that I just said about how much of it is molten at any given time, and that is how far off axis does the crust at Midocean ridges remain in this sort of semi-molten or mushy-like state? So how long is it hot, and for how far off axis is it hot? Aha, it does work, see? The bottom is preserved. Okay, so in the future, now you guys know, this one doesn't go all the way down, but those ones do. Okay, so one of the things that I want to try to quantify for us today is how long does this mushy zone at the mid-ocean ridge, the lower oceanic crust of mid-ocean ridges, does that remain in sort of a mushy-like state? And how can we possibly measure this? Okay, so I mentioned that we have done a lot of work on mid-ocean ridge crust and what does the oceanic crustal structure actually look like. And there are several different flavors of mid-ocean ridge. So you have things like the mid-Atlantic ridge, which are slow spreading. You have things like the East Pacific rise, which are fast spreading. And you have things like the Gackle ridge or Southwest Indian ridge, which are very slow, ultra slow spreading ridges. And each of those translates to a different proportion of the crust being magmatic and a different proportion of the crust being intrusive versus extrusive. So I just want to make clear that what I'm going to be talking about today is crust that is fast spreading ridge crust, like the East Pacific rise or the Nazca ridge, or these sorts of very fast spreading ridges which have a very nice magmatic structure. So these here are layered gabbros, so intrusive rocks, followed by the sheeted dikes and the pillow basalts. This is sort of the classical mid-ocean ridge crust, the Penrose model for oceanic crust. But that is not to say that this is universal for all mid-ocean ridges, just for fast-spreading ridges, because slower spreading ridges and ultra-slow spreading ridges have crusts that are significantly different. So today what I'm focusing on is what does the lower oceanic crust of fast ridges look like. And one great place to go and look at this is between 9 degrees and 10 degrees north in the East Pacific rise. And this has been a focus site for IODP and a lot of different research through the years, is this East Pacific rise between 9 and 10 degrees north. So in 2000, Dunn and colleagues went out and they measured the P wave velocities through the oceanic crust at the East Pacific rise between 9 and 10 degrees north. And what they showed was that you have a very slow region, which corresponds to hot. So in this figure, the hot is in red and the cold is in this sort of beige color. And that is when the P wave velocities are slower. Okay, so P wave velocities with depth in the oceanic crust, the magma chamber sits about here, and it's very hot near the magma chamber. And as you go off axis, you have sort of this broadly symmetrical hot region where the P wave velocities are slow. Okay, so what they came up with is that you can translate these slow P wave velocities into temperature anomalies. Okay, so they said this is probably what the isotherm, or what the thermal structure of the oceanic crust at 9 to 10 degrees north on the East Pacific rise looks like. So we have a hot region in here from the axial magma chamber at about 1 kilometer's depth down to the Moho at about 6 or 7 kilometers depth. So we have a very, very hot, above 1150 degrees C region, which has some steep isotherms coming off of it, and the crust quickly becomes cold after that point, okay, all the way down. So they interpreted these P wave velocities to be due to temperature, but also could be influenced by partial melt within the lower crust, and they can't, by this method, resolve between those two things, okay, whether it's just a temperature anomaly or whether it's temperature plus a little bit of partial melt. So along came Yang Zha in 2014, and they published some results having captured very fortuitously in 2007 a new eruption between 9 and 10 degrees north on the East Pacific rise. Okay, so this is from the same region as what the Dunn et al. Study showed, but using a different method. This is using the size of S-wave velocities in a method called seismic compliance. And so S-wave velocities don't penetrate through liquids. You can't make a shear wave go through any partially molten stuff. Okay, so if your S waves are higher, if you have a faster velocity of S waves, that means there's less melt around. And if you have a lower one, that means there's more melt around. Okay, so that's my very petrology-esque. Vadim gives me a thumbs up. Thank you. Good. Okay. So in 1999, they measured the VS profile between 9 and 10 degrees north, and they came up with this green line. And so this is depth below the seafloor. The axial magma chamber sits here again, right around 1.5 kilometers depth. And so your S waves shoot to 0 there because there's tons of melt around. And at around 1999, they measured this, okay? But they weren't able to use it to constrain what's going on until a new eruption happened in 2007. And what they saw was that between about 3 kilometers depth and 6 kilometers depth, or 7 kilometers depth, they saw a huge jump in S-wave velocity. And so this gives us very good reason to believe that that partial melt, or that sort of molten stuff that was down there, was getting tapped out of the oceanic crust during that new eruption in 2007. Okay, so they tried to put an estimate of how much melt is possibly down there before and after the eruption. And what they came up with was somewhere in the range of 5 to 25%. And this depends on whether that melt is in spheres or in thin films, or what the aspect ratio of that melt is within the lower crust. But really they can't do much better than somewhere between 5 and 25% of the mid to lower oceanic crust is partially molten, which then gets erupted out during these eruptions. And that they also said between 5 and 7 kilometers off axis. Okay, so in the Dunn et al. Study, they thought that things could remain partially molten about 2.5 kilometers off axis. But now with this seismic compliance, they're sort of pushing that out to about 5 to 7 kilometers off axis, that things are remaining partially molten. Okay, so these are great tools, but I don't think we've fully answered the question of how long, these are coming up with 2 different potential estimates. So how long can we maintain this partial melt in the lower oceanic crust? And how else can we constrain it, potentially using geochemistry instead of geophysics? So in order to quantify how long the lower oceanic crust remains partially molten, we need to know 3 things. First, we need to know the crystallization temperature. So that's, when do these crystals start crystallizing, this liquidus temperature? And then we need to know the solidus temperature. When are we completely solid? At what temperature are we completely, there's no more partial melt around? And then how long does it take in this area between when it starts and when it finishes? What is the cooling rate, or how long does it spend in this partially molten stage? Okay, so we need to know the crystallization temperature, the solidus temperature, and the cooling rate. How fast does it go from liquidus to solidus? And unfortunately, we don't have a place in the East Pacific Rise where we have the entire lower crustal stratigraphy completely exposed. And so we need to go places like the Oman Ophiolite, which are pieces of oceanic crust that have been thrust up onto land. In particular, the Oman Ophiolite was thought to represent a fast or intermediate spreading ridge, and so it's a good analog for looking at things like the East Pacific Rise and comparing with the East Pacific Rise. So this is the Oman Ophiolite. Muscat sits right around here. That's the capital of Oman. It's on the Arabian Peninsula, in case you guys don't know where Oman is. The stuff up here looks a little bit more arc influenced, and so we want to stick down in this lower Samael Ophiolite section in the south, because that's where we see features that look very similar to a fast or intermediate spreading ridge. And so, all these cartoons are great of what an oceanic crust actually looks like, but it's really nice to go out into the field and actually look at them. So here is the pillow basalts of the lavas getting extruded out onto the seafloor. Here you can see the sheeted dike complex that we have in the Oman Ophiolite. Here are the layered gabbros that I am going to be talking about extensively today. You can see they look almost like sedimentary rocks. They're so very well layered. And this section right here is a picture of the mantle peridotite that lies right below the oceanic crust in Oman. Okay, so in particular, we're going to look at the southern sections because those are less arc influenced, and we're going to be looking at the Wadi Khafifa section, right in the heart of this southernmost section. And I want to point out that I want to point out that there's a drilling project called the Oman Drilling Project that's funded by the Intercontinental Drilling Program, as well as IODP. So ICDP, IODP are both funding it. that I've been involved with. And that section is drilling a core, basically, through the lower oceanic crust in Wadi Gudea. And Wadi Gudea is about 50 kilometers to the west or to the east from Wadi Khafifa, where I'm going to be showing you a lot of the results. And one of the reasons why I picked Wadi Khafifa is because if you look at the cross-section that was done by Pallister and Hobson in the early 1980s, you can see that here's the mantle peridotite down here, the sheeted dikes up here, and the Wadi Khafifa section is relatively free of large offset faults and is relatively undeformed in terms of folding or anything like this, so abduction and placement processes. Whereas in the Gadir section and the Wadi Gudea sections where they're drilling currently, you can see there are a lot of large offset faults and some significant folding. And so that is a problem with some of the drilling that we're working through currently. Okay, so in the Wadi Khafifa section, I went through and measured all the plagioclase compositions and the clinopyroxene compositions. And again, when you think about anorthite compositions and magnesium numbers, for those of you who aren't petrologists, just think high equals hot and low equals cold, okay? So you can see that throughout the entire 4 kilometers of oceanic gabbros in this section, there is not a significant deviation from about AN 82 or 83. So the lower crust in the Oman Ophiolite, and likely in the East Pacific Rise, is very homogeneous in composition at about AN 82 or 83, and clinopyroxene numbers of around 80 to 85. Okay, so this in and of itself is a really important thing, because prior to this work, we didn't know whether there was a significant, stratigraphic change in compositions within the lower oceanic crust or not, which you might expect if you look at the comparison of mid-ocean ridge basalts to the cumulates that we can observe at the seafloor, at certain places, tectonic windows in extant ridges. So how does Oman, I want to prove to you that Oman is a good analog for looking at mid-ocean ridge processes, even though it is an ophiolite and therefore slightly strange. So if we look at those, if we put those plagioclase compositions and clinopyroxene compositions, this is really bothersome, huh? If we put those plagioclase compositions and clinopyroxene compositions into sort of a diagram next to all of the actual stuff that we can drill or we can find at the East Pacific Rise from tectonic windows and openings in the crust, we see that it looks very similar. It sort of overlaps with what we can observe from stuff that we can find on the East Pacific Rise. Okay, it's a little bit higher. On the higher end, we don't have a lot of these lower, more evolved things, but on a general whole, it looks very similar and overlaps with those data from the East Pacific Rise, from Pedo Deep and Hess Deep, these areas. Okay, so hopefully I have proven to you that using the Oman Ophiolite and the gabbros that we have, the gabbro crustal section that we have, is a good thing to be able to look at mid-ocean ridge processes in general. So again, we need to find 3 different things: crystallization temperature, solidus temperature, and the rate at which they went from crystallization to solidus. And we want to do this in the crust at each individual stratigraphic depth, because we want to know, is it going fast at the top and then slow at the bottom, or is it going fast all the way through? Okay, so to do this, first we have to find crystallization temperature. So to calculate this, there was a paper published just last year where they developed a new thermometer for getting the crystallization temperature of gabbros. And before this paper was published, it was very, very, very difficult to come up with a constraint on what time these gabbros were starting to crystallize. And so what they showed is that if we measure the plagioclase rare earth element concentrations and we measure the coexisting clinopyroxene rare earth element compositions, you can use the partition coefficients, so the way that the mineral absorbs rare earth elements from the liquid, follows a particular partition coefficient, which is called D, for a given temperature. And so if you know the plagioclase composition, then you can calculate the liquid composition from that if you know the temperature. But if you also know the clinopyroxene, those have to be in equilibrium with the same liquid as that plagioclase was, and therefore you can calculate the temperature at which both of those crystals were in equilibrium with that same liquid. Okay, so this gives us a great new way of calculating crystallization temperatures in coexisting phases. And it also gives me a great reason to use this lovely lab that we have here at Rutgers, the Laser ICPMS Lab. And if you guys haven't been by to see it, we set this up about 4 years ago. And what we have is a laser. This is the laser right here. We can put in our samples. You can sort of see them, kind of not very good pixelation there, but you can put a thin section of your sample in there, send a beam down and laser the section, aerosolize it through, and measure it here in our ICAP, our mass spectrometer. And we can get really nice resolution on trace elements and even uranium, lead, and zircons. So we did this, or I did this for all of the samples that we have from the Oman Ophiolite to measure the plagioclase and the pyroxene rare earth element compositions. And rather than showing you all of that data, I'm showing you here just 2 representative sections. So this sample here is very close to the sheeted dikes, so the top of the oceanic crust. And this sample here is right near the bottom, so near the mantle, the bottom of the oceanic crust. And you can see that their rare earth element patterns follow very normal trends for clinopyroxene, a nice europium anomaly in the plagioclase, and they look like good data. Okay, so when we use that plagioclase pyroxene rare earth element thermometer and we plug in these data here, we can calculate out a temperature of around 1230 for crystallization of that gabbro, and a temperature of about 1218 for the one down near the bottom. And without showing you every single one, here is the general summary. So we have from the moho down here at the bottom, this is the mantle, up to the top of the lower crustal section near the sheeted dikes up here, you can see that the gabbros come out somewhere between 1190 to about 1250, and there's not any stratigraphic change in their crystallization temperature. So it looks like the oceanic crust is crystallizing at roughly the same temperature, or it's beginning to crystallize at roughly the same temperature everywhere throughout the crust. It's not just in these melt lenses near the moho or melt lenses up near the top. It's crystallizing at the same temperature throughout. So this in and of itself is a really big discovery. We did not know this, and it was not predicted at all that you would crystallize, roughly the same throughout the entire stratigraphy. But I want to take it a step further and talk about this sort of persistence of this mush zone and use this data to be able to constrain something even bigger. Okay, so now we have, for each individual sample that we have in the Oman Ophiolite throughout that entire stratigraphy, we've got this crystallization temperature. So the next thing we need to do is find a way to measure the solidus temperature of each of these different samples. So the solidus is typically very difficult to constrain. And one way that people have tried to do it is to look at zircons. And titanium and zircon in particular gives a good temperature for when that zircon was crystallizing out of a liquid. Okay, so the titanium in zircon has been used significantly in Hadean zircons to try to understand magmatic processes back then, as well as many other places. But the problem with zircon is that there's not very much of it in mafic rocks. Okay, it's a very difficult mineral to isolate from mafic rocks. It's much more common to find in felsic things, granites and rhyolites. But in some locations, it has been found in mid-ocean ridges. So here is basically a compilation from Lissenberg in 2009, where he goes through and compiles all the data that's ever been published on titanium and zircon temperatures from all the mid-ocean ridges. And you can see that these record about 750 to 900 degrees C. And because zircons are not typically found in mafic rocks, we can use these temperatures as an estimate of the last moment of crystallization of these gabbros. They're not a cumulus phase. They're not coming out normally in a mafic rock, but they might be crystallizing in sort of the interstitial partial melt, that's sort of the mushy part. Okay, so the temperatures that a zircon records are very close to that last gasp of magma. That is probably the solidus temperature of that gabbro. Okay, and so we see from all of these different locations, and it doesn't really depend on spreading rate. Mid-ocean or the Mid-Atlantic looks very similar to the East Pacific Rise, looks similar to Southwest Indian Ridge. But we can see that they all come out between around 750 to 900, which is close to what we would expect for the solidus temperature. But because zircon is so difficult to find, it's not present in every single sample that you look at. So if we want to use zircon solidus temperatures in each of our samples in the Oman Ophiolite, it's going to be very, very challenging. So a better way is to actually look at a mineral called olivine. So olivine is found in every single one of these samples in the lower oceanic crust that I looked at. And there is a thermometer that was developed in 1990 actually for planetary samples called calcium and olivine. So it's basically recording the diffusive or the diffusion of calcium ions from an olivine which doesn't like calcium into clinopyroxene grains which really like calcium. Okay, and depending on the cooling rate and the amount of calcium in the system, this can give you a closure temperature for that diffusive chronometer. And this is something that we can use in every single one of our samples. And so while this is not particularly a solidus temperature, it is very close to when that gabbro has become solid. And if you look at the calcium and olivine closure temperatures through the Oman Ophiolite, again, this is moho down here, and this is the sheeted dikes up here. These are all those titanium and zircon temperatures that 700 to about 950 that I showed you before from the Lissenberg study. And these are all the calcium and olivine closure temperatures that we calculate for our samples in the Oman Ophiolite. Okay, so the gabbros have closure temperatures of calcium and olivine between 780 and 1000 degrees C. And so we know the rocks have to be solid by this point, and they must have just passed through their solidus. So this is a great way to be able to estimate the solidus for every single individual sample that we have in the stratigraphy. The great thing about calcium and olivine as well is that it also gives us a cooling rate. Okay, because it's a diffusive thermometer, it can be used to actually estimate how fast that calcium ion was diffusing between the olivine and the clinopyroxene. Okay, so if we know the peak calcium concentration and we know the size of the grain, we can plug it into the sort of classical diffusion cooling rate equation of Dodson, and we can calculate cooling rates for this calcium and olivine thermometer throughout the entire stratigraphy as well. And when we do that for all those samples, we get cooling rates here, and you have to again look, I'm really glad that these other two are down now. You can get cooling rates that look like this, from the top down to the bottom. And they're pretty fast, so this is the conduction only predicted line for if you're losing heat purely by conduction through the oceanic crust, that's what you would get. And our samples are clearly cooling faster than that. If we look at some other models of hydrothermal circulation and how quickly the crust likely cools, we get models from Turkaoui et al. That sort of model very, very rapid advection of heat out of the system due to hydrothermal circulation, which overlap very, very nicely with our data from the Oman Ophiolite, okay? And if we look at that Dunn et al. Study and use his isotherms to be able to calculate how fast you're going from above 1150 down to about 800 degrees C, we can calculate that those isotherms from the East Pacific rise from that P-wave velocity study that I showed you before look like they should predict a cooling rate that looks something like this. Okay, so our data are definitely fitting within the realm of fast hydrothermal circulation throughout the entire oceanic crust. No change with stratigraphic height, and they look very similar to what's predicted from the P-wave velocities and the East Pacific rise. Okay, so remember, I had originally said we wanted to know the crystallization temperature, the solidus temperature, and the cooling rate at each location in the crust to be able to constrain how long the crust remains partially molten. And so now we've got each one of those things. We've got the crystallization temperature here, we've got the solidus temperature in the blue here, and then we've got our cooling rates here in the black. And so if we put all of this together, we know that the time that the magma, or the time that the gabbros spent above their solidus is the liquidus temperature minus the solidus temperature divided by the cooling rate. And if we know something about the spreading rate of that ridge axis, then we can calculate how long, so we get the time basically from this equation. We know the spreading rate, we can calculate the distance off axis and compare that to what they saw in the P-wave velocity study and the seismic compliance study. So here is that final data in the green here. This is the Dunn et al. Prediction from the P-wave velocities. I haven't put the Za et al. Study on here because that's way out at 5 to 7 kilometers. But what we can say is that from the geochemistry, it looks like the crust is remaining partially molten about 500 meters to 1,000 meters, or 500 meters to a kilometer off axis in the Oman Ophiolite at least. And that means that this lower crust remains partially molten for on average about 10,000 years. Okay? So this is a really exciting new conclusion. We've basically shown that the entire lower oceanic crust remains partially molten for about 10,000 years, about a kilometer off axis, and there is no difference from top to bottom, that the stuff that we can image in the axial magma chamber is not making it hotter up near the axial magma chamber, and the stuff that we can image down near the MOHO is not making it any different. The entire oceanic crust is going through this process together as a cohesive whole. So what are the implications for this? Well, that Za et al. Study showed that the partial melt is leaving the system with each individual eruption. And the periodicity of eruptions on fast-spreading ridges is plus or minus 10 to 20 years. We've seen a few places where eruptions have occurred at about this interval in same location, 10 to 20 years, plus or minus. But those eruptions are tapping and homogenizing. This is all the mid-ocean ridge glasses that we've been able to measure. It's over 17,000 by now analyses of mid-ocean ridge basalt glasses, and they all come out very, very homogeneous in terms of composition. Those eruptions on the 10 to 20 years time scale are tapping magma that's been sitting around from anywhere from 0 to 10,000 years in the lower crust, okay? So things that we see erupted today on the seafloor have been sitting around since, the end of the last ice age, which is kind of an incredible thing to think about, these sort of large-scale things on this long time scale. The other implication of this is that all of this partial melt, we published a study back in 2015 looking at strain rates in the lower oceanic gabbros, and whether the strain that is accommodating the spreading of the oceanic crust, right? The oceanic crust is a plate, and it's spreading apart at the ridge axis. So all of that spreading and all of the strain associated with that spreading needs to be accommodated in just this very, very narrow, partially molten region of only 500 meters to a kilometer off axis. So all that strain from 200 kilometers worth, or 1,000 kilometers worth of spreading is actually being accommodated only a very, very narrow region of the oceanic crust. So this is another very important implication for how strain is accommodated during spreading. So with that, I am going to put up my conclusions. So I've put several different studies that I've been working on have sort of been woven through this talk, but the most important ones are that these are the first estimates of crystallization temperatures throughout the oceanic gabbros, and they are remarkably consistent from top to bottom. So that is the sort of the new stuff of the plagioclase conopyroxene rare earth element temperatures. Fast-spreading oceanic crust remains partially molten from between 0.5 kilometers up to 1.5 kilometers off axis, which puts the estimate slightly lower than all of those geophysical estimates that have been done on the East Pacific Rise. And these results have implications for the thermal structure of the crust and the construction and strain accommodation at divergent plate boundaries. So those are my conclusions, and I'm happy to take questions on that. I want to make one last slide where I talk about the things that I'm excited about looking into in the future. So I have been working on the oceanic crust for a while now. As Claude mentioned, I started working in the Oman Ophiolite during my PhD and have sort of continued that work till now. But another large part of my research profile or research program is looking at how the oceanic crust has changed. So we know all of these things about the fundamental observations that we can make on the Earth today about the oceanic crust. But what about when the Earth was slightly hotter in the Archean and in the past? And how does the oceanic crust record that or respond to those changes in the thermal structure of the Earth? And that's something that I've been working on extensively, looking at modern day oceanic plateaus, which are sections of the Earth's crust which are ultra thick oceanic crust, so may be a good analog for what the ultra thick oceanic crust in the Archean may have looked like. That has big implications for what the water budget of that ultra thick oceanic crust could have been back in the Archean. And has implications about how continents sort of first emerged in the Archean. So these are two things that the Archean continental crust formation, how continental building blocks come together and how they can be made out of processes of amalgamation of oceanic crust, oceanic plateaus, potentially subduction in the early Earth, and what that would look like through time. And then I'm, of course, going to continue all of the work with my students on timescales of magmatic emplacement and crystallization in big magma chambers, which I find really exciting. And particularly these ideas of looking at how fast these large subvolcanic continental magma chambers compare to things like oceanic crust formation. So what are the timescales, and are they any different in continental settings than they are in oceanic settings? And it's looking like maybe they are, maybe they aren't. There's some good evidence that places like the Bushveld have active hydrothermal circulation systems that also cool them off very rapidly. Okay, so with that, I will be happy to take any questions on the talk. Yeah.
Talk, especially since I talk about ocean crust more and marine geology.
You want to just take some slides?
I already have.
Oh, okay.
Here, I just all have. No, but I have a question. Like, so you're saying how important Oman is, and it's very interesting data as far as the temperature history of the lower crust. But we've sampled 1,500 meters of supposedly normal ocean crust at 35B. So my question to you is, do you look forward to doing this type of temperature analysis on 735B, and or is 735B normal or anomalous? How about that as really the punchline question?
Yeah.
That's in the Southwest Indian Ridge, which is one place that ODP has sampled the gabbros extensively, and at 1,500 meters of gabbro. This is Henry Dick's baby.
Yeah, of course, yeah. So Henry and I are good friends, and I have his samples, and the idea is to do these crystallization temperatures and the calcium and olivine on those. But 735B is a different spreading rate than E-specific rise in Oman. And so comparing, what are the crystallization processes in different spreading rates is another very important step for this work. So that's a proposal that I'm planning on writing.
It'd be interesting to see if your hypothesis is corrected. It should be at least uniform for the most part in terms of crystallization temperature, right over that 1,500 meters.
Yeah, so this is where some of the stuff in layered intrusions is actually sort of penetrating my work on mid-ocean ridges as well. So there is some thought that these big active magmatic systems might actually cool off faster than smaller magmatic systems. So it's a little bit counterintuitive, but if you have a bunch of magma entering the crust periodically, like in the East-Pacific Rise, where you have this large magmatic pulses coming up frequently enough where you can maintain a stable magma chamber. You also maintain a stable hydrothermal circulation system because you're always introducing this hot stuff that then speeds along the hydrothermal system. But if you have a slower spreading ridge where you have just blips here and there of magma, that magma might be actually able to cool down a little bit slower because there's not an active hydrothermal circulation system always taking that heat away, like there is in the fast spreading ridges. So it's not 100% certain which direction it would go with extending this to slower spreading ridges. You would think it would be faster in slow spreading ridges, but it might not be. The other problem is we don't know at what depth these things are emplaced in the, this is, particularly at mid-ocean or at mid-Atlantic ridge, you have a lot of these mega mullions where you have these low-angle detachment faults which bring up these lower crustal sections that we can look at. But in fast-spreading ridges, we don't have that. So it's not super clear from 735B or other places like these Kane megamullions and whatnot that those are really near the surface. Those could be magmatic emplacements at 7 kilometers depth or 10 kilometers depth instead of 1 kilometers depth, which would make a big difference for how the hydrothermal circulation gets penetrated through the mantle and cools that down as well.
Other questions?
Yeah.
Carl?
When you plotted the zircon temperature, published zircon temperature versus the calcium olivine temperature,
Yeah, here.
is the offset due to totally different data sets, or is it due to different recording of temperatures based on calcium and zircon? So it's not from the same samples, right?
They're not from the same samples. This titanium and zircon is this compilation.
That's what I thought. So is it a sample bias, or is it giving different results?
Yeah, it could be a combination. I mean, the fact that they find zircons in the samples at all is weird because these are mafic rocks. They are not zircon saturated.
But we don't have the calcium data from where the zircon data.
No, which would be a very helpful thing to have. But we don't have that.
If it's a common offset, then you can say what the zircon temperature probably was.
Yeah.
Calcium.
Yeah, I mean, one way to get the calcium temperatures to be faster than this is to make the whole thing crystallize really fast. So then you don't have tons of interstitial liquid that gets a chance to reach zircon saturation. So you have the zircon, or the interstitial liquid cools off really quickly, never really, it sort of quenches and never really gets to crystallize the zircon. And that also contributes to a higher closure temperature in the calcium and olivine system. And so these ones that are recording high closure temperatures are also the ones that are recording fast cooling rates. So that could be a reason why they're slightly offset too.
Jill,
Yeah.
I noticed that there's that kick in the temperature at the base of the crust.
Yeah.
What do you think about that?
Well, yeah, that's the problem. But we don't, I mean, it's a problem of only having 3 samples and not, it's nice that they all agree with each other. But yeah, I mean, I guess statistically, I don't know how to, I don't know that I would be confident yet in saying that this is a clear, like this is definitely a thing, that it's just higher in that topmost part, or that section there. I played around with statistics a lot when looking at this, and because it's such small numbers, it's not so obvious that it's statistically significant.
If I may, one last question. So in your model of the crust where you have the magma chambers, the sills all over, right?
Yeah.
They're not used to be,
Right.
They're thinking that they're just at the top. So what's gonna, so at any point in time when magma comes into the mantle, gets emplaced with the crust, what's going to determine its level of emplacement, whether it's high or mid-level?
Yeah, that's a good question. I mean, I think that the magma is going to go anywhere where it can. So there's no reason why it has to go all the way up to the axial magma chamber. If it's cold in a place and there's a crack, for instance, it'll penetrate that crack and expand the volume to accommodate itself. Or maybe there was a previous sill in that region and that was starting to crystallize and there's a little bit of partial melt still there, and so it finds that weakness there and inflates itself in that region. Yeah, and there's no reason why, given that the compositions, the plagioclase composition and the clinopyroxene composition, those are all uniform throughout the whole oceanic crust. There's no reason why a little parcel of melt couldn't go over here, a new parcel of melt could go over there. It doesn't all have to just be one pulse that gets intruded as a sill. It could be sort of making its way throughout the whole thing.
Related to that, I had a question about, well, isn't it a continuum from the axis, from the region axis away, and so therefore there must be some critical distance where you can shut things off or you can start to cool, but within a range you're still getting feed from the...
Yeah, exactly. So that's sort of what this is showing, is that range must be between a half a kilometer to a kilometer in thickness. Beyond that, it's too cold, everything's solid, and there's no reason why the magma, if it came up at 0, would want to go to 2 kilometers, if it can just sort of pond itself within that half a kilometer or whatever. But that's another thing, is that we have some constraint on how far it can be partially molten off-axis, because we see off-axis sills. We see off-axis volcanism in the seismic velocities as well. And so you can see, like, Suzanne Carbat's group, and now I'm forgetting, Shoshu Han was a PhD of hers, and Milena Marjanovic or something like this. They saw off-axis about 2.5 to 3 kilometers off-axis that you get these new emplacements of sills, which are to themselves a new body. And so it's crystallizing in a cold, solid crust, and they can image that's a solid body, or a new body of magma in a solid matrix. So that's a good constraint, pushing this partially molten zone, this on-axis partially molten zone, more towards what we're seeing in these, half a kilometer to a kilometer and a half of it being sort of partially molten. You agree with that, Vadim?
Sure, I agree with that. I was thinking here, pondering the overall amazing aspect of the fact that you focus all melt from however large volume into a region you can walk over in 10 minutes. Right?
Yeah.
And somehow it happens every.
Yeah.
You're saying, actually the question I had, the result that you got, that it's uniform, how, if you were to pick the entire ridge system, what fraction of it obeys this rule?
Well, for sure, the fast-spreading ridges, and so I guess that changes with time too, right? The proportion of the oceanic crust that's spreading fast versus slow may change through time. We don't have a good control on that, because unfortunately most oceanic crust older than 200 million years is gone. So, in the modern day, the Pacific, and in the past, we don't know.
Pacific and the Atlantic, I guess.
Well, the Atlantic is slower. The Atlantic is,
I was just curious to follow up on Ken's question, like whatever Henry Dick chose to throw.
Yeah.
Is it special or is it normal?
It's normal for slow spreading.
But it doesn't obey your rule.
It may not. We don't know yet. We don't know yet. Yeah.
I'd like you to elaborate more on why you think you've got a liquidus temperature from the Sinophyrexian plage.
Okay.
These two phases presumably are co-crystallizing all the way down through the solidus liquidus interval.
Yeah.
And should be freezing out at the low end of that rather than the high end of that.
Okay.
So where do you get the high temperature number from?
Right. Okay. So it has to be, so when we take we're never going to get to the first possible crystal that ever crystallized. Like, that's very difficult. I mean, you can figure out from the chemistry of that gabbro potentially, but the problem is that the gabbro is a cumulate which has then lost magma. And so you can't just take the gabbro composition and put it in melts or some other algorithm to figure out what the liquidus of that gabbro would be, because that wouldn't be the correct number because it's lost magma, right? So the best that we can do is this plage clinopyroxene rare earth element thermometer, where we know they must have been in equilibrium with the same liquid. And that had to have happened, yes, maybe it's averaging out from the high temperature to the low temperature end. So if anything, you could add a few tens of degrees more to this 1200-ish temperature. But that's not going to make a huge difference for the distance off axis, for instance.
Yeah. So those numbers are consistent with what you'd expect the phase equilibrium to be.
Yes.
Have you looked for zoning in either the pyroxene or the plage phase in terms of the rare earth that would a kinetic version of what you're talking about?
Yes. So that's a really good idea. So I did not look for zoning in the rare earth elements. We have the laser. The laser shot is 80 microns. The entire thing is only 2 millimeters. So I could get like maybe 4 points across and see if there's any profile there. But
even center and edge would be an indicator that might be useful.
Yeah, yeah, that's a good idea. I should look into, at least in a couple of samples to see if there's any zoning in those. Yeah, absolutely. The clinopyroxenes also, in some cases, have some exsolution lamellae, so that also plays like a little complication with all of that.
One other quick one.
Yeah.
Can you identify any pressure effect at the height of the column that you're dealing with?
No.
The calcium in olivine is very pressure sensitive, so...
Yeah, okay, but between 2 kilobars and 3 kilobars, there's not a huge effect there. Anybody else?
Well, this is a pretty good time to end, and so if there's no more questions, thank you very much, Joe.
Yeah, thank you.